In this presentation, we're talking about Sig Figs, measurement, and uncertainty associated with the measurements. So, what is a significant figure? And you guys, I'm going to post this, so you guys don't have to take notes on it now. Just pay attention. If you're having difficulty with the subject, which it takes a lot of practice. The more practice we do, the better we'll get at it. So just pay attention. If you want to take notes later, feel free. If you want to do an outline in class, just outline the topics that you want to take notes on later. That's fine too. Don't copy everything down though. I'd like it if everyone was giving me their full attention. So a significant figure is just a number that we know with reliability. We are measuring these numbers. That's it. That's all sig fig is. It's a number that we've measured. Okay? So, the rules for determining how many sig figs are in a measurement, what we're going to do, and the rule is, you're going to determine the measurement to 1 decimal place more precise than the graduation of the instrument. The graduation of the instrument is like the smallest increment. Okay? And that last place is it's estimated. And that's why we need to include our uncertainty. I believe I gave these rules to significant figures yesterday. Correct? I wrote them on the board, and I think most people took them down. Also, in the notes, they're also on the online notes. So, if it's a non-zero digit, it's significant. If it's a zero between non-zeros, it's always significant. Placeholders are not significant. Zeros after a decimal point and a non-zero digit are significant. So in A, we have 4 sig figs. B, we have 5 sig figs. C, we only have 2 significant figures, the 2 and the 5. And D, we have 1, 2, 3, 4, 5, 6, 7 significant figures. These guys over here. Remember, if it's before a decimal, these are just placeholding zeros right here. All right? We need to estimate our uncertainties. Okay? So, scientists, when you're communicating numbers, we need to know how well or how certain they are. And there's going to be a certain amount of error involved in every single measurement, and that's what we call uncertainty. So a lot of times what you care more about is how precise we can measure something. That is really what we try to do as scientists, is get more and more precise so that we can hopefully achieve more and more accuracy. Okay? And this is about how we do it. Why we study significant figures is how we talk about communication and measurements. Okay? So that's why we do it. We want to correctly communicate what we've measured or calculated. That's important, extremely important. Otherwise, when you're an engineer or a plane maker or a train engineer or whatever you guys end up doing, or if you're a pharmacist or in the pharmaceutical industry making a drug, you need to know and be able to communicate what you know correctly. So, if you take a look at this this is a thermometer right here. You're measuring this digit. So, the graduation here is 0.1 degrees Celsius. That means every increment goes up by 0.1 Celsius. So if I had this is, I think like 46, this line would be 47. The smallest increments are going to be 0.1. So this would be like 47.1, 47.2, 47.3. That's what I mean when I refer to the graduation, is the smallest increments that the instrument can measure. So the temperature we can read, it's higher than 46. This is our 46 right here. it's less than 47, right? We know that. We're going to estimate the last digit here is 47. We can read it to 46.8. So this is 46, and that's 0.8. That little graduation. Oh, it's actually pretty easy to see up on the board. Can you see that okay? To not be imaginative, or take a look at it later. So, oops. So we're going to actually, that can be measured to this spot. So we'll move on in just a second. So I'm going to actually, I messed up, and that should have said 46.80, and you guys will see why in a second. I'll change that. Let's come back to that. So these are rules for calculating when we're doing significant figures. I want to do a little bit of practice here, and we'll come back to a couple things later. When you're adding and subtracting with significant figures is we look to the least specific place in both numbers. Okay, and we're going to round to that least specific place. Okay? For multiplication and division, we look at the number of significant figures, how many there are, and we round to the least number of significant figures. Okay? So when we're adding and subtracting, just like when you're talking about regular addition, you look at the place. Multiplication, you look at the number moving forward. So I want you guys to try right now, try these calculations. Okay? See what you guys come up with. This will be our little warm-up for the day. So write these down. One technique that I found with addition and subtraction that works is just line it up like you always would and just draw a line where the least precise digit is in the calculation. So like this is to the tenths, this is to the this is to the hundredths, these two are to the thousandths. So draw that line there, and then you're going to round to the left of that. That's one technique that works for addition and subtraction. There's another example. Yes, Fawn?
So it doesn't really matter like what place it's in, like tens or hundreds. It just has to be the same amount as Sig Figs.
That is, for addition and subtraction, the place definitely matters. That's what all you're concerned about in addition and subtraction is the place. Multiplication and division, you're only concerned about the number of sig figs. Okay? So all you really have to do is know one of the rules, and the other rule is the other rule. Right? So you consider place and number. If you know that addition and subtraction is place, you know multiplication and division has to be the other one because there's only two rules. It's like all you have to do is remember which hand's your left hand. If I remember this is my left hand, this has to be my right hand. Right? Am I just strange? Okay. All right. So just get some practice with it. There's another example of, this number's to the tenths, this number's to the thousandths. We're going to round to the tenths in this number. It doesn't matter. This has 2 sig figs here. This has 4. My answer has 1. The number of sig figs doesn't matter in addition and subtraction. It matters the place. Just like we talked about when I added 12 plus 1. 12 plus 1 is 13, not 22. Addition, we consider the place. Right? You guys already know this. Okay? So think about what you know. Don't drive yourself crazy. Multiplying or dividing, we round to the number that is the least. So least number of sig figs. So we round to 0.13 here. Okay? We've done enough of these. So if you guys want some more practice, I'll post this up. You guys can try them tonight. Uncertainties. Let's talk about that. So there's a tennis ball. We're measuring it. What's the diameter of this in centimeters? Take a look. It's kind of tough for you guys to read out that. Shivani, would you mind just shutting off the lights? Not the ones on the side. There we go. Because I think it's these will be easier to see. Thank you. Keep on going. There we go. So, if you're measuring the diameter here, it's about 6.4 centimeters. Okay? You guys should be able to calculate that. But could also be like 6.3 or 6.5. Could even be 6.44. So when we actually do this measurement, you know, we're not exactly certain about the measurement. We don't know all of the numbers. So it's important that we record the measured numbers along with our degree of uncertainty. So all measured values have uncertainty. All of them. If you're measuring, it has uncertainty. If you're measuring and you're doing the reading, we'll talk about that in a second. But even if you're measuring with an electronic balance, that has uncertainty as well. So let's say the diameter of the tennis ball is 6.4 plus or minus 0.1 centimeters. This is our measured value here. And this is our estimated uncertainty. We'll talk about how we calculate that there. So whenever you have a measurement, every measurement should have two things in this class and for the rest of your life. Should have uncertainty, and it should also have this little hat here, units. So when you're writing a number, if you just write down a number, that's like 1/3 of the points. That's like 1/3 of what you need to do. You need to record your uncertainty as well as your units. It would be like going skiing without skis and a coat. You look ridiculous. Same thing as writing a number without units and uncertainty. Because you can't do that. So let's talk about our uncertainty also should be in the correct place. So this here measurement 6.4 and our uncertainty is 0.15. That really can't exist because your uncertainty is related to the measurement, and they have to be in the same place. So here, my uncertainty is in my hundredths, my measurement's in my tenths. That doesn't work. That's one thing that really jumps out to me. Also, and I know it's going to happen in our next lab report, but that's one thing I really see quickly is the uncertainties in the hundredths, measurements in the tenths. It's an easy thing for me to pick up. What's wrong with that? Same kind of thing. Our measurements in the ones, our uncertainties in the tenths. It doesn't work. And same thing here. This one is, I get a lot like this. This one I'm like, oh no, just what am I doing? This one, our measurements in the hundredths, our uncertainties in the ones. If you can measure to the hundredths, the uncertainty's got to be in the hundredths, not the ones. That drives me crazy. Please don't do that, guys. Please. What this really means is that the actual diameter is going to be between these two values with 100% certainty. There's no possible way that the measurement can be outside of that. That's really what 6.4 plus or minus 0.1 means. Does that make sense? Okay. So I'm communicating that. So our actual accepted value, which we don't know, you might not know the accepted value. So you don't know that, but we know that our value is there. Okay? Different instruments, I don't know if you guys have ever measured a distance with, like, there's the type of clamp ruler, which, you twist and then it goes down to measure it more precisely. Anyone ever use one of those? Sometimes you're using them with, like, when you're doing, like, precision measuring. So we can't be any more precise than this. So But let's go back to the thermometer. Okay? This here, we can read it to the 46. That's our 46 right here. And then 0.8. And I think if you guys can see, it's a little bit above the 0.8 right there. So our graduation is in the tenths. We're going to estimate that hundredth digit. And our uncertainty is going to be half of the graduation. This is for something analog that we're measuring. Okay? So if you guys can see that, this is my 46. Oh, let me project that on here. Right? So this is my 46. This is my 46 line. This is my 0.8. And the measurement is a little above that. So I estimated 0.05. Okay? So 46.85 is my measurement, degrees Celsius. And I need to include my uncertainty too. Half of 0.1 is 0.05. That's it. It's that simple. Okay? It's going to take practice though. We'll get plenty of practice. Yes, Grace.
So, like, no matter what, like, thermometer or like graduation they're using that is like that, it's always going to be like half of the graduation.
Yep.
Okay.
That's going to be half the graduation. Is going to be the uncertainty. All right. So, oh, I flipped these slides. That's okay. So, you guys understand? Is that clear? Okay. So, like, why don't you guys? I want you guys to write a measurement down for this guy right here and do centimeters. Fun. So, hopefully we got about 65 centimeters. Our last digit's in the ones, which is good. It should be, because our graduation is in the tens of centimeters. So, uncertainty would be half the graduation, so 5 centimeters. Half of 10 is 5. So, that's going to be what we're going to be doing in our class. Measurement 65 centimeters plus or minus 5. Now, I know with this one, this little ruler here, you could probably say with certainty that it's 65 or 64 plus or minus 2. For our course, stick to half the graduation. All right? It'll just make things easier for everybody. So if we were doing a little more measuring, we had a different instrument. This meter stick is to the 1 centimeter, right? This one is to the 10 centimeter. So they're different instruments with which you're measuring. So let's estimate this length now real quickly. 1. So this here, we'd say it's about 64.5. So I'd estimate it that because it's right in between the 4 and the 5 here. So we'd say 64.5. And my uncertainty was half the graduation, so it's going to be 64.5 plus or minus 0.5. Okay? Or if you said 65.0, that's fine as well. But notice how the uncertainty agrees with the measurement. Certainty in the tenths, measurement in the tenths. Good? All right. So, when we are calculating, we have to make sure that we take into account that both measurements have uncertainty. Okay? So, for instance, and this is with adding and subtracting. So, if I'm measuring the beaker plus copper weighs 123.4 plus or minus 0.1, and the student knows that the measurement of the mass is 113.8 plus or minus 0.1. If I'm calculating the mass of the copper, I really have to include this uncertainty. Okay? So my measurement is easy to calculate, 9.6. But anyone want to take a guess as to how uncertain it would be? What do you think, Brian?
2.
Not 2. Close. What do you think, Grace? 0.2. That's correct. So My answer for this mass of copper should be 9.6 plus or minus 0.2. How did we get that? We added our absolute uncertainty. So when you're adding and subtracting, all you do is add the uncertainty, and that's to find it out. Okay? This will be up there. So our mass of copper, 9.6 plus or minus 0.2. We got that from adding the absolute uncertainty from our measurement. Okay? Let's why don't you try this one real quick. So if we're adding these up, oh, there's a couple more. You know what? So this first one, we should have gotten 13.1 plus or minus 0.6. Okay? We'll do a couple other ones later, but that should be our answer for the first one. To end class today, nobody pack up. Stop backing up, everybody. It drives me nuts because we still have time. Okay? Class ends when the bell rings. So therefore, we shouldn't be packing up until class ends. Since class ends when the bell rings, we shouldn't pack up until the bell rings. When we're multiplying or dividing, it becomes a little more complicated. What we do here is we have to add our percent uncertainties. Percent uncertainty is just what percent the uncertainty is of the value. All right? We'll stop here, and that's it.